Record is pressed?
Yep.
All right. So topic 8 is going to be mathematical induction. We just finished introduction to mathematical proof. Induction is a particular type of proof that we're going to look at next. And the basic premise behind proof by induction is that we start off with a propositional function that we looked at in topic 1, in the topic 1 PowerPoint. We had propositional functions. We had propositions whose truth value depended on the variable choice. So in this particular case, the way induction works is we typically show that the proposition is true when the variable takes on a value of 1. The variables are going to be integer values. So we show that the proposition is true when the variable is equal to 1. We then assume that the proposition is true when the variable is equal to some value n, and demonstrate that if it's true when the variable is n, that it must be true when the variable takes on the value of n plus 1. So the basic idea is you want to show that your proposition has a set of solution integers. Typically, the set of integers for which the proposition will be true starts with the integer 1. You then assume that it works for some integer n, which is okay to do because you've shown that it works for 1. And then you demonstrate that if it works for n, it must work for n plus 1. And you show that it works for n plus 1 using your assumption that it worked for n. And if you do this, it proves that it works for all integers greater than or equal to the integer 1 that you started with. Mathematical induction doesn't necessarily need to start out with a 1 as being the first integer for which you demonstrate the truth value of p. So it could be that the set of solutions starts with some negative integer, perhaps, but you still then do the same process. You assume that given it's true for negative 2, if negative 2 is the first integer for which the proposition is true, you then assume that it's true for some integer n greater than negative 2, and demonstrate that if the proposition is true for n, it must be true for n plus 1, which then proves that the proposition is true for all integers. So probably the easiest way to show this is with an example. So example says, conjecture a formula for the sum of the first n positive integers. Then prove your formula using the principle of mathematical induction. So this is kind of the classic first example that you show to students when you introduce the idea of mathematical induction. So the idea here is to guess a formula for the sum of the first n positive integers. The way that you can conjecture or guess a sum is to start with some smaller set of integers and try to come up with a clever way to add them. And in this particular case, what you want to notice is that if you take the first integer and pair it with the last integer, so in this case pairing a 1 with a 6, if you add those two together you get a 7, and then you work your way in from the endpoints. So the next integer over is a 2, I walk it over, I pair it up with a 5, 5 and 2 is 7, I walk in an integer from each end, I pair the 3 with the 4, I get to 7. And so the idea is that if I'm given a string of integers, if I pair the first integer with the last, that sum will repeat itself over and over again as you work towards the center of the summation. So in this case, to get the sum of the integers 1 plus 2 plus 3 plus 4 plus 5 plus 6, I can take 7, which is the sum of any pair of integers as I work my way inwards, and I want to multiply it by the number of pairs I get that give me a 7. So in this case, there's 6 integers altogether being added, which means I'm going to get 6 divided by 2 is 3 pairs of 7s. Or in this case, 7 times 3 is 21. The next step, to generalize this, we want to think about taking the sum 1 plus 2 plus 3 plus ... out through plus n minus 2 plus n minus 1 plus n. Take the sum of the first n into positive integers. If you pair them up, you get pairs again. The last integer plus the first integer is n plus 1. If I then move in 1 on each ends, here I get 2 plus n minus 1, but 2 plus n minus 1 is going to be n plus 1 again. I then I move in one more time. If I do 3 plus n minus 2, I'm going to get n plus 1 again, and I can work my way in towards the center of the data set. So I can see that the sums I get are n plus 1s, and then I have to ask the question, how many pairs of those will I get? Well, I'm going to have n total integers in the summation divided by the 2 integers it takes to make a pair, and I'm going to conjecture that my sum adds up to n plus 1 times n divided by 2, where n divided by 2 gives me how many pairs of n plus 1s I get. So in summation notation, I'm going to conjecture that if I take the sum from I equal 1 to n of I, that this summation 1 plus 2 plus 3 plus ... plus n is just going to add up to n plus 1 times n over 2. I do that based on inductive reasoning, and then what I need to do then is use the principle of mathematical induction to prove that this formula n plus 1 times n divided by 2 actually gives me the sum that I want. So this is always going to be a 3-step process in most cases. Step 1 is going to be show that the formula that you conjecture works in the simplest possible case. And the simplest possible case would be for n to equal 1. Take the sum from I equal 1 to 1 and make sure that the formula works in the simplest possible case. Step 2, so let's write this down. Step 1 is going to be show it works when n equals 1. Step 2, in the induction process, assume it works for n equals k, where k is some integer usually greater than 1. And then step 3 in the process, show that given the assumption in step 2, the assumption being that the formula holds when n is equal to some integer k, show that given the assumption in step 2 that the formula holds for n equals k plus 1. If I do this, then I show that the formula works for all positive integers, 1 through n as n goes to infinity. So this is a 3-step process, just like in the previous lesson where I indicated that we needed to write the proofs formally in paragraph form. We'll need to do that again, but my suggestion typically is to bullet step the proof and make sure everything works before you try to write it up nicely. So if I bullet point the proof, step 1, you let n equal 1. This is the simplest possible case. Well, then the summation is going to be the sum from I equal 1 to 1 of I is just going to equal 1. The formula, n plus 1 times n over 2, if we plug 1 into it, we get 1 plus 1 times 1 over 2 is 2 times a half is equal to 1. And this indicates that the formula works in the simplest possible case when n is equal to 1. Step 2. Assume it works when n is equal to k. That is, assume that the sum from I equal 1 to k of I is given by plug the number k into the formula. K plus 1 times k over 2. Plug k into the formula. K plus 1 times k over 2. There's step 2. Step 3 is use your assumption to demonstrate that if it works when n is equal to k, it must work when n equals k over 1. Or show that given your assumption that it works when n equals k, show that it must, given that assumption, work when n equals k plus 1. And I don't really have a spot for step 3 here, so I'm going to bullet point my step 3 on here. So step 3, we want to let n equal k plus 1 and use our assumption to show that the formula is still going to hold. Okay, so one thing that you can do to help yourself with an induction problem is to identify what it is that you need to show. So in step 3, we're going to assume that n equals k plus 1, and we need to show that using our assumption we'll get the same result that we would have gotten if we just plugged k plus 1 into the formula that we think works. So an important step, I think, is a need to show step, where you identify what it is that needs to happen for you to complete your proof. So in this case, if the formula is true, when we take the sum from I equal 1 to k plus 1 of I, and if we were to actually plug k plus 1 into the formula, we would get k plus 1 going in for n. We'd get k plus 1 is k plus 2, and then we would replace this n with a k plus 1, and it would be over a 2. So this is what we need to show. If the formula works, this should be what we get. And it is helpful sometimes to expand this out so that when you see it happen, you recognize that you're getting what you need to show. So if we multiply these two binomials together, we're going to get k squared plus 3k plus 2, and it will all be over the 2 in the denominator. Okay, so once we've demonstrated what we need to show in our step 3, where we assume that n is equal to k plus 1, we can come over and bullet point our step 3, where we say, suppose n is equal to k plus 1, and then lay out what you know must be true. So in this case, we're finding the sum from I equal 1 to k plus 1 of I, which is the sum given by 1 plus 2 plus dot 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 plus all the way out to k plus an extra k plus 1. In step 3, you always need to use your assumption from step 2 that the formula worked for n equal k. So when I look at the summation I have here, I have the sum 1 plus 2 plus dot 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 plus k. From my inductive step, step 2, we assume that the formula works for this sum right here. So the sum 1 plus 2 plus dot 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 plus k can be gotten using the formula, which is the n plus 1 times n over 2 formula. So we replace n with k, we get k plus 1 times k over 2, plus we have this extra k plus 1 this time. So we add him on, k plus 1. And what we need to do is to show that this can be manipulated to look like what we need to show, so that we can work backwards to the form we would have gotten had we used the formula directly. So here we need a common denominator. We'll multiply this by 2 over 2, which will give us something over 2. We get k times k is k squared, plus k times 1 is k, plus distributing the 2 in, we get 2k's plus a 2, which gives us a k squared plus 3k plus 2 all over 2, which is what we needed to show. So this demonstrates that our formula is correct, and all we have left to do is to write this up nicely. So that's the final part, and maybe the most difficult part. So I'm going to write this proof up formally. All right, so now we're going to do the formal writing up of the proof by induction. So I'm going to start off by saying that I'm doing my proof, and like we did in the previous lecture, we are going to tell the reader what our proof technique is going to be. So our claim was that the sum from I equal 1 to n of I is given by n plus 1 times n over 2. So we'll start off our proof by saying let n equal 1, and so I'm writing up, trying to formally write up step 1, which is where we let n equal 1, and we showed that the summation and the formula gave us the same result. So let n equal 1, and note that the sum from I equal 1 to 1 of I is just 1. And 1 plus 1, replacing n in the formula with a 1. 1 plus 1 times 1 over 2 is equal to 2 times a half is equal to 1. So because it's a proof by induction, and I'm telling the reader it's a proof by induction, they're going to expect to see this step where I start off with the easiest possible case, the case where n is equal to 1. Step 2. Now we write up step 2 of the proof. Now, assume that for n equal k, you want to assume that the formula works. Assume that for n equal k, the sum from I equal 1 to k of I is given by k plus 1 times k over 2. So there's the assumption step. Extend pane. Step 3 is always going to be, now let n equal k plus 1, and show that given this assumption in step 2, that the formula will work for k plus 1. Finally, let n equal k plus 1. It follows that, now we're going to do a little bit of math. It follows that we were taking the sum. We're taking the sum from I equal 1 to k plus 1 of I, which is going to equal, now we show them what the sum looks like, 1 plus 2 plus 3 plus dot 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 plus k plus the next integer k plus 1 equals, we know that the sum from 1 through k is given by our formula, k plus 1 times k over 2, plus we have that extra k plus 1 sitting there. We get our common denominator, which is going to give us k times k plus 1 plus 2 times k plus 1 all over 2. Not showing as much work this time, because when we bullet pointed our proof, we showed the work. Extend pane, simplify this product. This simplifies to, what does it simplify to? K squared plus 3k plus 2 all over 2, which equals, what does that equal? That factors as what? K plus 2 times k plus 1 all over 2. And this is exactly what we would get if we plugged in. Now I can stop there actually. Don't know why I'm bothering to keep going. This is what we identified as the thing that we needed to show. We said if the formula works and we put I equal 1 to k, from 1 to k plus 1 of I into the formula, we would get this. And we just showed that we, using our assumption, did get exactly what we would have gotten had we used the formula, so we are done. So, thus, by the principle of mathematical induction, the sum from I equal 1 to n of I does equal n plus 1 times n over 2 as desired. And give it a tombstone. We have the sum of the first n consecutive odd integers. Conjecture a formula for the sum and prove it using mathematical induction. So probably you should also say here the first n positive consecutive odd integers. That should probably be in there as an additional instruction. So in this case, you explore it the same way that you did the sum of the first n integers. You think about, well, what's going to happen if I have the sum of odd integers? And we can play the same game that we did on the previous slide, where we took the sum of the first and last integer, which gives us a 12, and then move in 1 and do 3 plus 9, which gives us 12, and then move in 1. And we get 7 plus 5, which gives us a 12. And if there are n integers, there will be n divided by 2 integer pairs. So in this case, there are 1, 2, 3, 4, 5, 6 odd integers. 6 divided by 2 will give us the pairs of integers, and we'll go 12 times 6 divided by 2 is 36. And then we just want to generalize this to the sum of the first n odd integers. So we've got the sum 1 plus 3 plus 5 plus ... plus, and then the nth odd integer is going to look like 2 times n minus 1. In other words, when you plug 1 in here, you get 2 times 1 is 2, 2 minus 1 is 1, so when n equals 1, you get the first odd integer. When n equals 2, you get 2 times 2 is 4, minus 1 is 3, you get the second odd integer. So this expression or rule, 2n minus 1, always generates the nth odd integer. And the game that you play is you pair up the first integer with the last. So 2n minus 1 plus 1 gives you 2n. And you conjecture that the pairs of odd integers will always generate 2 times n. And then you further conjecture that there are going to be n divided by 2 pairs of them, and the 2's then cancel, giving you n squared. And so we make the conjecture, that the sum from I equal 1 to n of the first n odd integers, and each odd integer looks like 2n minus 1, we conjecture that the sum adds up to n squared. It'll be the same 3-step process to prove this. We show it for the simplest possible case. So step 1, show the formula works when n equals 1. In other words, when you're taking the sum of the first odd integer. And if we do that, the n squared would give us 1 squared, which is 1. And the summation formula would be the sum from I equal 1 to 1 of 2n minus 1 would just generate 2 times 1 minus 1 is 1. So the formula and the summation give you the same thing when n is equal to 1. Step 2, assume for n equals k that the sum from I equal 1 to k of 2n minus 1, assume that this is going to equal, use the formula, k squared. And then step 3, show it holds for n equals k plus 1 using your assumption in step 2. Using the step 2 assumption. Except you need to spell assumption right. So in step 3, to do that, we just directly calculate the summation. We take the sum from I equal 1 to k plus 1 of twice n minus 1, and we expand that summation out. We say, hey, this is going to be 1 plus 3 plus ... plus. For the kth positive integer, it's going to be 2k plus 1 plus. Now we need the k plus first, which is going to look like 2 times k plus 1. Whoops, this should be a minus 1. It should be 2k minus 1. And this should be 2 times k plus 1. Replace n with k plus 1, and then it's a minus 1. And we need to show that using our assumption that this is going to generate the same thing that we would have gotten by plugging k plus 1 directly into the formula that the sum should be just given by n squared. So again, this gets back to that need to show. What is it that I need to show? For n equal k plus 1, we need to show that the sum from I equal 1 to k plus 1 of twice n minus 1 is going to look like k plus 1 squared is what we would get if we use the formula. So not using the formula, we should be able to manipulate into a form that looks like k plus 1 squared, the form we would get if we directly use the formula. And if you expand k plus 1 squared out, we get k squared plus 2k plus 1. So we're looking to manipulate into this form, which then lets us work backwards to the k plus 1 squared form that we need to show. So using the assumption, the sum of the first k integers, which is given by 1 plus 3 plus dot 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 plus twice k minus 1, we can use the formula for that sum. So we should be able to calculate the sum of the first k by doing k squared if the formula is correct. Plus, we have this little extra piece here, 2 times k plus 1 minus 1, where we plugged in the k plus first integer. And we want to simplify this out. This would be k squared plus 2k plus 2 minus 1, or just k squared plus 2k plus 1, which is just k plus 1 squared, which is what we would need to show. This is what we would get if we used the formula. So show using your assumption that you would get the same thing as if you used the formula, which then demonstrates the formula is correct. So we laid out a bulleted step 1, step 2, step 3, and now what we need to do is write up the formal proof of it, much the same way that we did a moment ago. So our proof will be by induction. So we're going to let n equal 1. Show it works for the simplest possible case. Then, well, we know what that's going to look like because we pre-worked it out. We know that we're going to get 1 squared equals 1 from the formula, and the summation, using the summation directly, is going to give us a 1 as well. Then 1 squared is 1, and the sum from I equal 1 to 1 of twice n minus 1 equals 2 times 1 minus 1 equals 1. So the formula works in the simplest possible case. That's always your step 1. Now, assume that for n equals k, assume that the formula works. The sum from I equal 1 to k of twice n minus 1 is just going to be given by k squared. Step 3. Now let n equal k plus 1. Now we need to show that using our assumption we get the same thing that we would have gotten had we used the formula directly. So now let n equal k plus 1. It follows that the sum from I equal 1 to k plus 1 of twice n minus 1 is equal to 1 plus 3 plus dot 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 plus twice k minus 1. There's the kth odd integer plus 2 times k plus 1 minus 1. There's the k plus first odd integer equals. And then we know by our assumption that the sum of the first k odd integers is just given by k squared plus, we have this extra k plus first odd integer sitting there, plus 2 times k plus 1 minus 1. Now we simplify. When we simplify this, we get k squared, and we already worked it out over here. We get k squared plus 2k plus 1, k squared plus 2k plus 1, which is just the square of k plus 1, which is what we needed to show. Therefore, now we can draw our conclusion. Therefore, the sum from I equal 1 to n of twice n minus 1 does just equal n squared, and we can end the proof. Okay, so we'll try to do this a little bit more compactly this time without bullet pointing the steps. And this one, the flavor of it will be a little bit different than the first two. So in this case, we're asked to show that n is less than 2 to the n for all positive integers n. So positive integers 1, 2, 3, 4, etc. So again, if we're doing an inductive proof, you start off with the easiest possible case, and the easiest case is when n equals 1. So note that for n equal 1, here's the claim. Note that for n equal 1, 1 is less than 2 to the 1 is true. That's true, right? Now, assume that for n equals k, assume that k is less than 2 to the k. There's step 2 in the induction process. Now step 3 will be to let n equal k plus 1 and show that given our assumption, k plus 1 must be less than 2 to the k plus 1. Finally, let n equal k plus 1. And what I want to do is pause for a moment, and I want to think about what it is that I need to show. So again, I need to show something. What is it that I need to show? What do I need to show? I need to show that k plus 1 is less than 2 to the k plus 1. And I want to recognize that 2 to the k plus 1 is the same as 2 times 2 to the k using our exponent rules. Same base, the product of same bases raised to exponents, we simplify that by taking the base and raising it to the sum of the exponents. So this is what I need to show. If I can get it into this form, I can put it into this form, and I want to demonstrate that k plus 1 must be less than 2 to the k plus 1. This is what I need to show, and I have to show it using my assumption in step 2 that k is less than 2 to the k. So in this particular case, I can say, note that. So here what I'm going to do is different than what I did previously in that I'm going to use the assumption directly. Note that k is less than 2 to the k by assumption, which means if I add 1 to each side, if we add 1 to each side, the inequality should still hold. And now I want to notice that as long as k is greater than or equal to 1, which it will be because we're working with positive integers, that the left-hand side is going to be less than or equal to 2 to the k plus 2 to the k. That's a horribly written k. 2 to the k plus, and I still wrote it terrible. Let's get down here on one knee. 2 to the k plus 2 to the k. So this statement will be greater than or equal to the previous statement because 2 to the k is going to be larger than 1 as long as k is greater than 1. But this is just equal to what? Well, this is 2 times 2 to the k because we have 2 of them. And then if I sneak over onto the other board because I'm out of room, I can say that it will be equal to 2 to the k plus 1. So the final result is that the k plus 1 that was less than the right-hand statement here is going to have to be less than the 2 to the k plus 1 statement on the right-hand side. And this is what we needed to show. So I can say as desired. And that ends the proof. So in this example, we want to show that n cubed minus n is always divisible by 3 as long as n is a positive integer. So n would be equal to 1, 2, 3, 4, etc. So again, there'll be a proof by induction. And step 1 is always going to be to prove that things work for the simplest possible case. Whether that case starts with n equals 0, n equals -2, n equals 12, it doesn't matter what it is. Show that it works for the simplest possible case that you have to demonstrate. In this case, because we want n to be a positive integer, I'm going to start with n equal to 1. And I'm saying by induction, so the reader is expecting me to start with the simplest possible case. So I say let n equal 1, then we get what? 1 cubed minus 1 is 0, and 0 is divisible by 3. It's kind of a boring case. But 0 is nevertheless divisible by 3, so things work in the simplest possible case. Step 2, make an assumption. Now assume that for n equals some integer k, typically greater than 1, assume that k cubed minus k is divisible by 3. Now move to step 3. Let n equal k plus 1 and use your assumption to show that k plus 1 cubed minus k plus 1 must be divisible by 3 as well. Now let n equal k plus 1. follows that, k plus 1 cubed minus k plus 1 equals, now we can expand this out, so we're cubing a binomial, so we could do that using the binomial theorem or Pascal's triangle. So the coefficients are going to be 1, 3, 3, 1. So from here I'm going to get k cubed plus 3k squared plus 3k plus 1 minus k minus 1 by distribution, minus k minus 1, distributing the minus sign into the parentheses. Now simplify things. We get k cubed plus 3k squared plus 3k. 1 minus 1 is 0, and we're left with the minus k sitting here. Regroup things, put the k cubed minus k together. K cubed minus k plus, put the k squared and the k together and factor the common 3 off, plus 3 times k squared plus k. We want to look at this for a minute and identify that we have something that's divisible by 3. This term is divisible by 3 because it's a multiple of 3. And k cubed minus k is divisible by 3 by our inductive assumption. We assumed in step 2 that if n equals k, that k cubed minus k was divisible by 3. Therefore, by our assumption, k cubed minus k is divisible by 3. 3 times k squared plus k is divisible by 3. Therefore, the sum of two things that are divisible by 3 must also be divisible by 3. Therefore, k cubed minus k plus 3 times k squared plus k is divisible by 3 because each of the terms is divisible by 3. And I can end that. So on this slide, we want to demonstrate that for all non-negative integers n, so non-negative means starting at 0 this time instead of 1, because 0 is a non-negative integer. We want to demonstrate that the sum 1, which we want to recognize 1 is the same as 2 to the 0. We want to show that 1 plus 2 to the first plus 2 squared plus 2 cubed plus dot 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 plus 2 to the n can be added up by just doing 2 to the n plus 1 minus 1. Or in other words, we're trying to show that the sum from I equals 0 to n of 2 to the I is given by 2 to the n plus 1 minus 1. We want to show that this formula is correct, that it holds. So step 1 in this case would be to let n equal 0. Step 2 would be to assume that it works for n equal k. And then we would need to demonstrate that it works for n equals k plus 1 using our assumption. You always have to use the step 2 assumption in the process of completing step 3. This is a good one where it is good to know what you need to show. And what you're needing to show in the step 3 of the inductive process is that 1 plus 2 to the 1 plus 2 squared plus dot 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 plus 2 to the k plus an extra 2 to the k plus 1 can be given by using the formula directly, which would give you 2 to the, replace n with k plus 1, 2 to the k plus 1 plus the extra 1 minus 1, which is 2 to the k plus 2 minus 1. This is what we would need to show. Need to show this right here. So we'll step over, start our proof here. So our proof will be by induction. So we're going to let n equal 0 this time. The base case, the smallest n can be, is 0, not 1 this time. Let n equal 0. Then, what do we get? We have the sum from I equals 0 to 0. We're just putting 0 in this time. I could probably just put the sum from I equals 0 of 2 to the I will be equal to 2 to the 0 equals 1. And the formula that we're given would give us 2 to the 0 plus 1 minus 1 equals 2 minus 1 equals 1. So it holds for the base case. The formula holds for the base case. Now, assume that for n equals k, the formula works. The sum from I equals 0 to n of 2 to the I, the sum from I equals 0 to k of 2 to the I is just given by 2 to the k plus 1 minus 1 using the formula. Now let n equal k plus 1. It follows that, now we do the summation, the sum from I equal 0 to k plus 1 of 2 to the I is given by 1 plus 2 squared plus dot 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 plus 2 to the k plus 2 to the k plus 1, because we have that extra term in there this time. But these first ones, the sum from 1 plus 2 squared plus dot 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 plus 2 to the k, we assume that the formula holds for it, so that that summation right there is just 2 to the k plus 1 minus 1 from our assumption step. So we can replace the first k terms, or first k plus 1 terms, with 2 to the k plus 1 minus 1. And then we still have a plus an extra 2 to the k plus 1, which equals, now there's 2 of these, they're exactly the same, so it's 2 times 2 to the k plus 1 minus 1. But the exponent on this base is a 1, so we can combine into a single base by adding the exponents. K plus 1 is k plus 2 minus 1. Which is what we needed to show over here. We worked out ahead of time what we needed to show if we were to use the formula directly. So extend the pane, or in other words, bring my writing up to the top and say which is what we needed to show, and call it a wrap.